Right, I want to show you this. It's a differential equation, but it's a differential equation that a GCSE student would understand from what you've done already. Okay? Okay. So, oh gosh, I gotta stop saying okay. Right, x squared plus y squared equals 25 squared. Let's say 5 squared. Oh, something just disconnected. Oh, what's disconnecting here? Keep going. So we have here the equation of a circle, x squared plus y squared equals r squared. And because there's a 3, 4, 5 triangle, I can put a point here like 3, 4. To get to this point from the origin, you have to go across 3 and up 4. Across 3 and up 4. So we know that the gradient of this line here must be 4 divided by 3. And if we wanted to know the gradient of this tangent, then we could do the negative reciprocal. So that would be, instead of 4 over 3, that would be minus 3 over 4. But what did we do there? We ended up with the gradient of the tangent being minus the x value divided by the y value. So let me just write that over here. First of all, we started with x squared plus y squared equals r squared. And then we found out that the gradient at some point, the gradient of the tangent at some point on that circle. That's my phone ringing. Stop recording. Okay, so we found out that the gradient of the tangent to the circle was equal to minus x over y. And in A-level calculus, we call the gradient at some point on a curve, we call it the derivative, and we write it dy by dx like this. So this is a differential equation that should be pretty familiar. Essentially, not familiar, but it should make sense to someone who's studying GCSE maths. Dy by dx equals minus x over y. I want to show you how we solve something like this. We rearrange it and we write y times dy equals minus x times dx. And then we use an A-level technique called integration, where we write it like this. Big kind of curly S, which used to stand for summa, S-U-M-M-A. It's like the sum. It's how we find the area under curves. So the integral of y with respect to y is equal to minus the integral of x with respect to x. So that's integration. We integrate this, which if you can, this is how I think about it. This is y to the power 1. This is x to the power 1. You increase the power by 1 and divide by the new power. And then here, you increase the power by 1 and divide by the new power. And then you have to add a constant. And that we've almost finished. So check this out. If I multiply both sides by 2, I get y squared equals minus x squared plus 2c. Add the x squared to both sides, you get x squared plus y squared equals, we'll just say some kind of constant. So we'll just write the constant as c squared. And look, we solved the differential equation and we got the equation of a circle. Boom. So this tells us, so if we didn't know where that differential equation came from, but we knew how to solve differential equations, we could solve it and it would tell us that the general form of the solution is of some kind of circle. And it can be any circle depending on the value of c. And then finally, this is getting into A-level, this is a really good way. Once you've solved a differential equation, you can actually check you got the right answer. So let me rearrange this. So I'm going to change this now. So it says y squared equals c squared minus x squared. And I'm going to take square roots really carelessly and just write it like this. Not even writing the plus or minus. And then I'm going to differentiate this, which is another calculus method that's used at A level to find the gradient of the slope of some function. So I'm going to write dy by dx. And now I'm going to have to differentiate c squared minus x squared to the power a half. Okay. And when you differentiate something like this, you bring the power to the front. You reduce the power by 1. And then you multiply by the derivative of the thing inside the brackets. So dy by dx equals, and then scroll up some more. Okay. And we get our final form. No, not quite. We get dy by dx equals, right, half times minus 2 is minus. So we've got minus x over the square root of c squared minus x squared. In other words, dy by dx is equal to minus x over y. This was equal to y. And I wanted to mention that I'm pretty sure Richard Feynman said something about, it was either about integrals or differential equations. He said they're really easy to do as long as you know the answer. And I think that's really applicable to differential equations. But in this case, I felt like we were able to complete the circle where we were able to figure out that a circle would have a differential equation of dy by dx equals minus x over y. We were then able to solve that to show that it does apply to circles generally. And then after we'd solved it, we then rearranged the circle equation and differentiated it to finally get back again the differential equation of gradient, that's dy by dx equals minus x over y. So I'm conscious that I started with GCSE and then I went into integration and then I did differentiation. But think about these as signposts towards things that you could learn about now if you want to get ahead of the A-level. Or if you're an A-level student studying differential equations, hope you found this interesting as well, because I think it's really nice when you can make connections across different topics. And I think it's pretty nice to be able to connect together gradient of a tangent of a circle with a differential equation. All right, that's it from me. Thanks a lot. Bye.